Jai Hind students, welcome to my YouTube channel. Students, smile is the electricity and life is a battery. Okay, again I'll repeat this statement. Smile is the electricity and life is a battery. So whenever you smile, the battery gets charged and a beautiful day is activated. So I repeat students, smile is the electricity and life is a battery. So whenever you smile, the battery gets charged and as a consequence, a beautiful day is activated. So students, the essence is keep smiling always, whatever be the circumstances. Clear? So spread happiness and you will get happiness in back. So that's action-reaction concept. So well students, let's come back to this particular session. We are going to discuss in this episode paramagnetism on the basis of atomic theory. In the previous lecture, we have discussed diamagnetism in detail. Diamagnetism that was discussed on the basis of electron theory. Here, we will discuss paramagnetic substances, its properties and the temperature dependency of paramagnetic substances. Now students, you all are aware, every matter is made up of atoms and molecules, isn't it? And every atom possesses a central positive core which is known as nucleus, surrounded by negatively charged electrons revolving around the nucleus, having both orbital motion as well as spinning motion, isn't it? And we are aware students, the revolution of electron around the nucleus that constitutes tiny current carrying loops, as a result of which each atom possesses some magnetic dipole moment in case it has unpaired electrons. If the atom has got paired electrons, as was in the case of diamagnetic substances, then what happens is the magnetic moment due to the orbital motion of an electron around the nucleus get cancelled out by the other electron of the same pair having orbital motion along the nucleus but in the opposite direction. So those two magnetic moments due to the electrons forming a pair being oppositely directed and equal in magnitude tend to get cancelled out. So net magnetic moment of a diamagnetic atom is 0. But students, remember, in the case of paramagnetic substances, each atom possesses unpaired electron. I stress on this particular point. Each atom of a paramagnetic substance possesses unpaired electron. Right? So as a result, what will happen is, due to this electron, which is unpaired electron of an atom, due to its orbital motion around the nucleus, it will constitute a tiny current loop. So as a result of which, the atom will possess some non-zero finite value of magnetic moment. So each atom of a paramagnetic substance, due to presence of unpaired electron, possesses magnetic moment. And as a result, each paramagnetic atom may be considered to be an atomic dipole. So students, thus every paramagnetic atom possesses non-zero magnetic moment. That is, it possesses some finite value of magnetic moment. And since each atom possesses some finite value of magnetic moment, therefore, each paramagnetic atom will behave as an atomic dipole. Therefore, each paramagnetic atom behave as an atomic dipole. I hope these 3 points are clear. Again I repeat students, unlike diamagnetic atoms, paramagnetic atom possess unpaired electron. So due to the orbital motion of this unpaired electron around the nucleus, it will constitute a tiny current loop, as a result of which each paramagnetic atom possesses some net finite non-zero value of magnetic moment, right? And since each atom has got some non-zero finite value of magnetic moment, thus each paramagnetic atom will behave as an atomic dipole. It will behave as an atomic dipole. I will represent it like this. This is the atom, and this arrow indicates that it possesses some sort of magnetic moment, obviously directed from south to north. So this will be the atomic dipole, right? So now what to do is, in the absence of any magnetic intensity, in the absence of any external magnetic field, these atomic dipoles, in the case of a paramagnetic specimen, they are randomly oriented. Due to the thermal agitation, these atomic dipoles are randomly oriented. That is, they do not have any preferred direction of alignment. They are randomly oriented. I will show you with the help of this diagram. So suppose this is a paramagnetic specimen. It is a paramagnetic specimen. Now what to do is, we consider the first case whereby the external magnetic field or magnetic intensity is absent. H is absent. H is equal to 0. You are aware, students, H is the magnetic intensity, isn't it? In air or vacuum, H magnetic intensity is given by B naught divided by mu naught. That is, B naught is equal to mu naught into H. Both are proportional to each other. So, in the absence of any magnetic intensity or in the absence of any external magnetic field, B naught is 0. What happens is, this is a paramagnetic specimen. All the atom will possess some net magnetic moment, but these atomic dipoles will be randomly oriented due to thermal agitation in the absence of any external magnetic field. So, diagrammatically, it can be represented in this particular manner. These are the atomic dipoles, and they all are randomly oriented. These all are randomly oriented. Clear, students? So here, the net magnetic moment is 0. So although, students, each atom of a paramagnetic material possesses some net magnetic moment, but when we talk about the specimen, when we talk about the paramagnetic substance as a whole, then it will contain several numerous atomic dipoles, and due to their random alignment, due to their random orientation, due to the thermal agitation, the net magnetic moment of this paramagnetic specimen in the absence of any magnetic intensity of the external magnetic field will be 0. No doubt regarding this. Because magnetic moment is a vector quantity, and these all vectors can be used to represent the sides of a polygon, all taken in the same order, and the vector sum will naturally be 0. So again I repeat, students, in the absence of any external magnetic intensity or external magnetic field, the atomic dipoles of a paramagnetic specimen are randomly oriented. They do not have any preferred direction of orientation, as a result of which the net magnetic moment of a paramagnetic specimen in the absence of an external magnetic field is 0. So it will remain unmagnetized. Now what we will do is, we will place this paramagnetic specimen under the influence of changing magnetic field, where the external field can be gradually changed, or rather the magnitude of the external magnetic field can be gradually increased. So let us place this paramagnetic specimen under the influence of changing magnetic field. Changing magnetic field means where the direction of the external field is considered to be same, but its magnitude is changed, or rather it is increased gradually, right? So it's like this. Suppose the magnetic intensity is gradually increased. This is it. Here it will be made to increase further. So gradually the external field is increased. So this is shown by the increase in the length of the arrow representing magnetic intensity. It is still increased, and here suppose the strength of the field is maximum. Clear, students? So what we have assumed is, we have assumed the same paramagnetic specimen to be kept under the influence of a magnetic field whose magnitude is gradually increased. So this is scenario 2, 3, these are the different cases, 4, 5 and 6. Clear? Now what will happen, students? These are the atomic dipoles. We are aware whenever an atomic dipole comes under the influence of an external field, then it experiences a torque, and the torque, due to the torque, the atomic dipole will tend to align itself along the direction of the external field. This is a very basic concept which you are already aware of, isn't it? I repeat, whenever a dipole, atomic dipole, a magnetic dipole, whatever you say, is under the influence of an external field, then it tends to experience a torque, and as a result it aligns itself along the direction of the external field. So when the field is smaller, when the strength of the external magnetic intensity or the external magnetic field is smaller, then they will tend to orient themselves. They will slightly tend to, these atomic dipoles will slightly tend to orient themselves along the direction of the external field. Now look, the orientation is somewhat symmetrical now. All the atomic dipoles are attempting to align themselves along the direction of the external field. Right? They are starting to align themselves in a particular direction. So now it is slightly magnetized. It will develop its own magnetic moment, but that will be too small, right? So it will develop its magnetic moment, but it will be very, very small. It will get magnetized, but it will be very small. So magnetic moment developed, or the intensity of the magnetization. M is the magnetic moment of this specimen, and I is the intensity of magnetization. Clear, students? I is the intensity of magnetization. And intensity and magnetic moment, they are proportional. Intensity of magnetization is defined as the magnetic moment developed in this specimen per unit its volume. So volume of the specimen will remain same. With the increase in the magnetic moment, the intensity of magnetization of the specimen will also increase, isn't it? So both M and I, they are proportional. M stands for the magnetic moment, I stands for the intensity of magnetization. Now, third case. Now the external field is still increased further. So what happens is, now the alignment will be more symmetrical. It will be more towards the external field, along the direction of the external field. So what happens is, here the magnetic moment increases further. So intensity of magnetization also increases further. Just concentrate on the length of the arrow representing I, which is the intensity of magnetization. The gradual increase in the length of the arrow representing I indicates that with the increase in the magnetic intensity, the intensity of magnetization of the specimen also increases. Right, students? It is further increased. So the alignment will further try to perfectly align itself along the direction of the magnetic field. Like this. So the magnetic moment of this specimen increases. As a result, the intensity of magnetization further increases. Still further, if the strength of the external field is increased, H, which is the magnetic intensity, is increased, then again the atomic dipoles, now it almost tends to align perfectly parallel to each other, almost. So here the magnetic moment of the specimen will further increase, resulting in an equivalent increase in its intensity of magnetization. Now students, a stage will come when all these atomic dipoles will get perfectly aligned parallel to each other and along the direction of the external magnetic field. That is when we say that it has attained the stage of magnetic saturation. So, suppose this is the external magnetic field at which the atomic dipoles becomes, or it orients itself perfectly parallel to the external magnetic field. Okay, this is the perfect orientation of the atomic dipoles. All the atomic dipoles here are perfectly aligned parallel to the direction of the external magnetic field, right? So here the magnetic moment would be maximum, and accordingly the intensity of magnetization of the paramagnetic specimen will be also maximum. So this is the perfect alignment of the atomic dipoles when they are aligned perfectly parallel to each other, and that too along the direction of the external magnetic field. So this stage corresponds to magnetic saturation. Magnetic saturation means beyond this, the intensity of magnetization or magnetic moment of the specimen can't increase, even if you try to increase the strength of the external field H. Still, the value of I will remain constant, I max. It has become constant. It can no further increase, right? So this stage corresponds to magnetic saturation. So case 6 represents magnetic saturation. It is the stage at which all the atomic dipoles inside the paramagnetic specimen are aligned perfectly parallel to each other, and that too along the direction of the external magnetic field. So as a result, now what happens is this end, this will acquire south polarity, and this end, it will acquire north polarity. So now it is magnetized. So basically students, what we have concluded is a paramagnetic specimen in the absence of any external field will remain unmagnetized. The net magnetic moment of a paramagnetic specimen in the absence of external magnetic field is 0. But as it is kept under the influence of gradually increasing magnetic field, then what happens? It will start getting magnetized slowly and steadily and gradually. And at a particular stage, when all the atomic dipoles of the paramagnetic specimen becomes perfectly aligned parallel to each other and parallel to the external field, then it is said to have been magnetized to the maximum possible extent. And that is when the stage corresponds to magnetic saturation. Clear? Okay, now before such magnetic saturation, it is found that consider all this, before this magnetic saturation, it is found that with the increase in the value of H, the value of I also increases. It's pretty evident from the diagram, isn't it? So before such magnetic saturation occurs, it is experimentally studied that the intensity of magnetization is directly proportional to the magnetic intensity. Clear, students? With the increase in the value of H, which is the magnetic intensity, the intensity of magnetization of the paramagnetic specimen also increases. It's pretty evident from this particular diagram. Also students, what will happen if you increase the temperature, if you heat this paramagnetic specimen? What will happen? Obviously, due to the thermal agitation, due to the fact that it will gain in thermal energy, so it will start vibrating more vigorously. So due to that thermal agitation on acquiring thermal energy, the alignment will again start getting disturbed. Its perfect alignment will get disturbed. So again, it will start aligning in random direction. So what I mean to say is that as the temperature is increased, the intensity of the paramagnetic specimen goes on decreasing. Because of the fact that with the increase in the temperature, due to the gain in thermal energy, the atomic dipoles starts vibrating more vigorously. So as a result, their orientation get disturbed and they again start orienting themselves randomly. So mathematically, we can state that the intensity of magnetization of a paramagnetic specimen is found to be inversely proportional to the temperature of the paramagnetic substance in absolute scale. Whenever temperature is written as capital letter T, so it should be understood that temperature must be measured in absolute scale. So T is the temperature. T is the temperature of the specimen in absolute scale. It is the temperature of the specimen in absolute scale. Clear, students? Do remember it. So you can combine these two. So from 1 and 2, what do you get? I is intensity of magnetization is proportional to H by T. Isn't it, students? In order to eliminate this proportionality sign, we need to introduce some constant. So further, it can be represented as I is proportional to, or rather, if you eliminate this proportionality sign, we need to introduce some constant. C is constant. C is known as Curie temperature. C is known as Curie temperature, right? C is a constant known as Curie temperature. C is Curie temperature. It's a constant. So, what do we get? It can be stated as I by H is equal to C by T. C is the constant which is known as Curie constant or Curie temperature. What is I by H, students? I by H is the magnetic susceptibility. You must remember the aptness or readiness of a specimen to get magnetized under the influence of some external magnetic field. That is known as magnetic susceptibility. And mathematically it is defined as the ratio of intensity of magnetization to the magnetic intensity. Therefore, students, what we get is okay, what we'll obtain is now I by H can be written as magnetic susceptibility. I by H is magnetic susceptibility. So therefore, I by H is equal to C by T. So I by H, just now we have discussed its magnetic susceptibility, written like this, chi m. It is C by T. C is constant, isn't it? Therefore, chi m is inversely proportional to the temperature of the paramagnetic substance in absolute scale. This is actually known as Curie's law. It is known as Curie's law in magnetism. So what will be the statement of Curie's law? Curie's law states that the magnetic susceptibility of which magnetic material? Of paramagnetic material. The magnetic susceptibility of a paramagnetic material is inversely proportional to the temperature of the paramagnetic specimen in the absolute scale. So this is known as Curie's law. So with the increase in the temperature of the paramagnetic specimen, the magnetic susceptibility will decrease. And obviously, at a particular temperature, when all the atomic dipoles becomes randomly oriented and attains its initial stage, then what happens? The paramagnetic substance in such a condition will tend to lose all its magnetism. It will said to get demagnetized, right? So anyway, this is Curie's law in magnetism. So one thing to be noted is that diamagnetic behavior, it is independent of temperature. Diamagnetic behavior is independent of temperature, but paramagnetic behavior, that is paramagnetic materials, does depend upon temperature. For paramagnetic substances, the magnetic susceptibility is inversely proportional to its temperature in the absolute scale. Clear, students? So this was about paramagnetism on the basis of atomic theory. There are various examples of paramagnetic substances like aluminium, chromium, sodium, manganese, right? Liquid oxygen. So these all are the examples of paramagnetic substances. We will discuss some properties of paramagnetic substances when we discuss the difference between para, dia and ferromagnetic substances. So that we will discuss in the coming lectures, right? So that's it for this particular session. Do join me in my next lecture. In that lecture we will be discussing ferromagnetism on the basis of domain theory. So till then, bye-bye and do take very good care of yourself. Thank you.